Okay, so before I start proceeding for ये use कर सकते हैं? नहीं. So before I start proceeding for op-amp topologies further, because your one of the assignment is on the layouts, so I think that is remaining. How many assignments you have covered in the lab? 3. First, second. Second is on layout. So first, third, and fourth. First and third. So second is not completed. So only 2 you have completed. Okay. So today, Divya, you will call me. I'll come for the lab. I'll see what you people are doing. Okay. So you can come at 3:30. Okay. Now layouts I'll be discussing so that you can finish the second assignment. And fourth assignment I have posted. So start working on it. In all, I would be giving you around 6 assignments. Each one on design and one on layout. Third assignment is on GM by ID technique. I hope you all have done that. It's a technique which can be used for designing purposes. Okay? So instead of doing things iteratively, normally we follow a design methodology. GM by ID is one such method which can be used. There is a journal paper on GM by ID also which you can refer. I will also post it or I will email it to you so that you can go through the whole methodology. So there is a journal paper on it, okay? So that you can have a good idea of GM by ID technique, okay? So today I shall be giving you a flavor of the analog layout techniques. So currently we are withholding the op-amp discussions wherever we are at the current status. And I will, in this lecture, I will be dedicating to the layouts. So how to draw good layouts. Okay, so since this, I cannot use paper and pencil, so you have to bear with me and we will be reading it through the slides only. Is it fine with the Goa campus? Yes. Yes, please?
Yes, ma'am.
Okay, so we are looking at how to draw the layouts. Now you all have done ICFT course. Integrated Circuit Technology, Fabrication Technology course. So there we know that there are process variations. Process variations may be because of mask, misalignment, maybe because of various, the overetching effects, undercutting, overetching, all those things are there. Okay, diffusion processes where the boundaries they change because of isotropic diffusion, isotropic nature of the diffusion. So boundaries are something that we have less control. So I cannot control the absolute dimensions, that is what we all know. Because absolute dimensions they change, has the current which is dependent on the dimensional parameters, W, L, T, ox, that value also changes. So in order to refine this method, in order to get a good stability or reliability, I cannot say that my Q point is shifting. I can't say that. Or that my current drive is varying, because of which the gain is changing or Q point is shifting. So there is a window. So process variations, they have to be taken care of. So normally process variations are taken care of at the layout level, because there is where you use certain techniques in order to lessen the parasitic capacitances, in order to get a near constancy in the drive current. So how to control dimensions? Certainly absolute dimensions you cannot change, but it is a ratio that we control. So let us understand that what are the 2 conditions because of process variations as it is listed. So you have mainly that overetching errors. Overetching errors coming into picture, overetching, undercutting, or if I look at the diffusion process, then the diffusion moving in an isotropic way in all the 4 directions, thereby increasing the length and width of your drain and the source junctions. Okay, it is moving beneath the gate oxide also, so that the total length is changing from the mask length. So all these processes, deviations are known as process variations. These are because of the inherent nature of the chemical processes, which we cannot control. We have little control on that. As a result, these things are given to me as a set of guidelines by the fab engineer or the foundry that these things will happen. So while you do your design, you please take care of those things. So that if diffusion is going to happen. I will increase my mask length so that ultimately the channel length I will have, even after overlapping diffusion areas, I will still have the required value of the channel length. So I can take care of those things at the design stage. Okay, so when we come to the matching, now because matching is very, very important, we have seen whether it's a current mirror, or it is a biasing, or it's a switch capacitor circuits, or it is a differential amplifier op amps. So we know that matching is required. Okay, so the question is that how to get a good matching, because normally we assume matched components, but rarely we get a matched component. If we do not give proper attention, I will not be able to get a matched components. So there are certain techniques which we use for getting a matched component, and for this we need to actually match the surrounding environment around those two components. That is known as a boundary condition matching. Okay, so there are 2-3 things. How to have a control on the ratio of the matched devices or the dimensions. How to have a matching 100%, nearly 100%, by matching the boundary conditions. Okay, and how to lessen the parasitic capacitance. Because at the drain junction, I do not want a very high parasitic capacitance. So all these 3 issues, they are addressed at the layout level. Okay, so how do we go about that? Let us understand. So if I have to make a certain layout, these are the layouts that we usually make. Do you have any practice of drawing layouts? You have. Okay, so these are all layouts. So now suppose you have to make a layout, as I am showing over here. A MOS transistor you have to lay out. Okay, so this is going to be the polysilicon, that is a gate. So it is a top view, so you have to now keep on understanding the cross-sectional diagram also. Keep on visualizing the cross-sectional diagram also, side by side. So we have a gate structure. So beneath this will be oxide, beneath it will be silicon. So there would be an MOS structure. This is going to be your source junction. This is going to be the drain junction. And then we have design rules which says that if there is a contact, it should be 2 lambda by 2 lambda. We are following the lambda based design rules, and there should be an extension of lambda from all sides. Okay, and then you should have a minimum distance of 2 lambda between contact and the polysilicon. So these are few design rules that we take care of while we do the design. Okay, so that means the minimum junction depth length has to be 5 lambda. Minimum junction. Am I clear to Goa campus?
Yes, ma'am.
Goa campus student, is it visible? Is it audible?
Yes, ma'am.
Yes or no?
Yes, ma'am.
So you people are having, do you people have an idea of layouts?
Yes.
Yes, please, yes.
Yes, ma'am.
Okay. So we have minimum junction length of 5 lambda. And minimum junction width should be of, again, 2 lambda plus lambda plus lambda, that is 4 lambda. So you cannot have junction length other than this, as per this figure that I have taken, based on the design rules. Now suppose you have to create a big transistor. Now suppose I have to create a big transistor. So let me take a big transistor. Let me show you a big transistor. I think I have it here. No, it's not here. Sorry. So visualize a big transistor now. Now you have to visualize it because I cannot show you how to draw. So visualize a big transistor. Suppose this width is, say, maybe 80 lambda. Now visualize it in your mind. Goa campus, Nisar, I think, Nisar, Srinivas. Are these people there? Akash, Mansa, Kirti, all these people are there?
No.
Somehow I'm not able to hear you properly. Is there some problem with the? Is there some problem with the camera and that? Or yes.
Yes, ma'am. We are here.
Okay. So now you also have to participate with me. So I request you to visualize that this width is 80 lambda. Everybody should have it in mind. So this lambda is 1 micron. This width is going to be 80 micrometer. And this can be minimum, say 5 lambda or 5 micrometer. Clear? and channel length is say 2 micrometer. Clear? Or 2 lambda. May visualize this in mind. Everybody has visualized. Now this 80 micrometer. Now if I ask you to compute the parasitic capacitances, this is what you have. So we have, how much would be the area? Compute. What is the area of this junction? Suppose this is your drain junction or source junction. What would be the area of this junction? It would be 80 micrometer multiplied by 5 micrometer or 80 lambda by 5 lambda. Clear? Okay. Now if I know total capacitances are proportional to Cj area plus Cj side wall. So if I have a certain Cj area, that would be multiplied by 80 into 5 lambda square. 80 into 5 gives you 400 lambda square. Cj0, that is the area component, multiplied by 400 lambda square. Please visualize. Plus the side wall capacitance. How much is the side wall? That's the perimeter. How much will be the perimeter? 2L plus W. We are neglecting the capacitance facing the channel region. So this gives you how much perimeter? 110 lambda into Cj side wall. Clear? You have two capacitances, Cj area and Cj side wall. Clear? Is this clear? I hope you all understand what we mean by side wall capacitances, area capacitances. You have learned about them. Okay. So now, if I compute this value, there would be some parasitic components. Now if I want to reduce it, suppose this is, I do not want a very large capacitive loading. In analog, that means a high time constant, that means a large, that means a very small pole. You may end up in having a small dominant pole, too many dominant poles will be there. I do not want a very large pole. So I want capacitances to be reduced. So I want to reduce its capacitance. So what should I do? What should I do to reduce its capacitance? So one way is that you do not fabricate a very large width, because large width means the total area is going to be very large, 80 lambda square. Here I have taken an example of a width of 80 lambda. So net total width is going to be 80 lambda square. Rather, you work with smaller width. But smaller width is, I cannot get the current drive. If I choose a smaller width, I cannot get a current drive. So what is the way out? What we say is that you do not get a W of 80 lambda made. Rather, total current should be sum of currents through each sum of current, where each current is corresponding to 20 lambda by 5 lambda. That is, you break a larger transistor into small transistors. That is, create a large transistor by using many small transistors. That is, I am going to show you the kind of structure that we are going to use is that make a large transistor by using many small units. Many small units. So where is that? Oh. Yes, here. Look very carefully. I am not making a large transistor. Rather, I am breaking each large transistor into say 5 or 4 transistor, so that total sum is corresponding to 80 lambda by 2 lambda, where each gate width will correspond to how much? 20 lambda by 2 lambda. So that 20 lambda by 2 lambda, this is also 20 lambda by 2 lambda. So when you add the currents through each of them, this will give you a current of total 80 lambda by 2 lambda. This is what I am going to get. So make a bigger component by using many small components. And all components that you are using, they should be standard, they should be same, they should be matched. So that it is simply an extension of one current component multiplied by 4 or 3. That is possible only when you have a matched components. So make a larger component. Here the component is going to be a transistor. Make a larger transistor by using many small transistors. Okay, so this is what leads to multi-gate fingered layout. Because there are many gates now. I will have 4 gates. Actually, I want to create a one transistor, but I would be getting a single, it implemented by using 4 small unit transistors, I will say. Unit does not mean W by L is unity. No. Unit means a block, a unit block, a standard unit that I have chosen for myself. It may not be the standard unit for you. It's for me. I have chosen a certain standard unit for myself, and then I'm keeping it same. I'm not changing it. In that layout. Clear? So make a bigger transistor by using many small unit transistors, and each of them is going to be the same. So we have to ensure matching. I have to ensure matching. So now this is the approach that I am going to use. So how to create this structure? So now I am going to show you how to create. It's going to be only on the slide. So you have to bear with me. Okay? Because this is something that I am not adept to. Okay. Let me show you how to start doing a bigger transistor of 80 lambda by 4 lambda. I actually split it into 4 transistors, each of width 20 lambda by 2 lambda. Okay. So what I do is that actually I take a width. Let me change the color so that you can, because this is possible for me to change the color. So let me take an active which is of green in color. So I have an active, okay, an active region. This width is going to be how much? 20 lambda. Lambda I am not writing, that is understood. I am going to have 20 lambda. Now there are going to be 5 gates. So I have 5 fingers. Let me choose red now. Red will be 5 poly. So I will have the first gate. Now you have to increase, you have to expand it. Okay, or should I draw it like this? 1, okay, 1 finger. This is second finger. This is third finger here. Not a very good layout, but I think I am able to give you the idea. And this is fourth finger. Make it like this, 4 fingers. That is why the name is given as multi-fingered gate layout. And then all the gates, they must be common, because all transistors must be parallelly connected. So their gate should be common. They should have a common gate. So this is a common gate. This is a common gate. All fingers are connected together. That is why the name is multiple gate fingered layout. Now, once this is done, I have to have all 4 transistors, drain same, gate same, and source same, because they have to be connected in parallel. So what should I do? So now I start making points, drain and junction. So let me choose a color so that you can find out. So let me make it as let this be the source. If this is a source, this would be the drain. This would be the source, this would be the drain. So I choose this as the source. So this has to be the drain. Now drain and drain has to be common for these 2 fingers. So this must also be the drain for second finger. So this is my first finger, this is my second finger, this is my third finger, and this is my fourth finger. So if this is a drain, so drain for this second MOS means this must be the source. So this must be the source, third finger also. This must be the drain for fourth finger, this must be the drain. This must be the source. How many drain regions you have? 1 and 2. Purposely I have taken this as a source. I could have started with this as a drain also, but then I would have had 3 drains and 2 sources, and normally drain is the output region. I want less capacitances at the drain region, so I should choose, or I should have lesser number of areas constituting drain region. Clear? Goa campus?
Yes, ma'am.
Okay. Clear? Huh? So we have got, now I have marked the points. Now all I need to do is only make the connections. So let me choose a blue color. Let me choose a blue color. Blue color is for connections. Okay. So I have to connect all the drains together. So I have to take so here you have to have a blue line, blue metal, and this is blue metal. And you have to make a contact here. I am showing it by putting a cross. A contact between green active and say metal 1. Similarly, a contact here between green active and metal 1. Now remember, so here if you make a contact here, so contact to poly separation must be 2 lambda, and contact to poly separation this side must be 2 lambda, and contact is 2 lambda by 2 lambda. So this total junction length has to be 6 lambda. 6. And remember, this is going to be 20. Width is going to be 20. This you have to remember. Similarly, so all drains are connected together. So this is going to become my common drain. This will act like a common drain. And now I can choose, say, a different colors, different blue color, so as to highlight the connection for the sources. So source here, so this is a connection here, you have to make a source. So this is source, okay, a source connection here. So a source down and a source connection here means a source down. Maybe I can, another metal. Now this metal, they are all connected and they can overlap poly, because in between is going to be silicon dioxide. So overlap does not mean a connection. Metal can overlap polysilicon. We all know that. So I have got now a multi-fingered gate layout of a big transistor whose width is 80 lambda and whose channel length is 2 lambda. Going by the design rules, if I look at this difference, it is going to be how much? Length? 2 lambda plus 5 lambda. So this is 5, this is 5 lambda. This is 6, this is 6, this is 6 and this is 5. So can you compute the total drain area? So it is going to be 6 lambda by 20 lambda. Total drain area multiplied by 2. Because this is a drain junction, this is drain. Add them together. The two capacitances will add them together. So total drain area is 6 lambda into 20 lambda. Total drain area, junction area. So this 20 lambda into 6 lambda, 120. Lambda square into Cj area. Remember, this is how we compute capacitances. Parasitic capacitances, C drain to bulk plus C side wall. What is the side wall capacitance of this area? 6 plus 6 only, because I have to neglect the face which is side which is facing the channel. So it is only 12 lambda. So total, if I take two junctions, yes, Akash from Goa campus, is it understood? Do you understand that? So there are two junctions, each one having a parameter of 12 lambda. So total parameter becomes 24 lambda. And total area becomes 240 lambda square. Yes, Manasa, is it clear?
Yes, ma'am.
So can you visualize what calculations I am making? So total drain area is with me, total source area is with me. So it is 240 lambda square multiplied by Cj area plus 24 lambda multiplied by Cj side wall. Compare it with the original values of 80 lambda. Compare what was the original values for 80 lambda single transistor. Yes, Kirti must tell me how much is the original area.
The area for 80 lambda was 400 lambda square.
And here it is 240 lambda square. See the difference. And how much is the perimeter initially?
110 lambda.
110, and here it is only 24. So can you see the difference, that in what drastic reduction in C drain to bulk? By doing the layout very carefully, we can actually reduce the parasitic capacitances. So multiple gate fingered layout actually is a way to reduce parasitic capacitances, and it is nothing but an approach where we are making a bigger component by using many smaller matched unit components. Many smaller matched unit components. Clear? Is this clear? Yes, Divya? And Vasanta? Yes, Apurva. So this is what I feel is that everybody should know how to calculate, and then your task will be to draw the layout in your lab and actually calculate the capacitances and obtain the capacitances through simulations also. You should obtain the capacitances in SPICE. Everybody is using ELDO? ELDO everybody is using, so ELDO, or you are using Spectre. Whichever you are using, you have to estimate the capacitive effects. Okay, so this is one way of reducing parasitic capacitances. This is also bringing the other methodology of making a bigger component by using many small components. So where does this strategy, making a bigger component by using small components, also helps us in controlling the W by L ratio of the two matched components. This also helps in that. How? So as we know that dimensions, they change. So I go back now. So dimensions, they change. You cannot do anything. Do have less control on that. So dimensions, when they change. So suppose this is, I have a geometry where I want a certain dimension x and a certain dimension y1. But because when it is etched away, say it is a polysilicon, you only keep the polysilicon near the gate area, then rest of it is etched away. Okay. However hard you try, even 1 nanosecond difference, there would be an over-etching. We normally pre-calculate the time for which etching has to be done. But even then over-etching does happen. So I may end up in having a smaller length, where I have a delta error here and a delta error on this side because of over-etching. So we are getting a 2 delta error, 2 delta E, reduction in the size. Same thing is on the width side also, because etching is an isotropic process. Etching is an isotropic. You dip the chip in a chemical solvent and then it etches away. Wherever there is no mask, that is etched away. Where there is no photoresist, it gets etched away. Okay. So we have an error. So actual dimension is changing from x1 and y1 to x1 minus 2 delta E and y1 minus 2 delta E. Now think of a situation where you have W by L of say 2, and I am creating my length is say 20 micrometer by 10 micrometer. So you are getting a ratio of 2. But this 20 micrometer, suppose it changes to 18 micrometer. After over-etching, I intend to create a 20 micrometer. Because of over-etching, I am getting it to 18 micrometer. Maybe 1 micrometer is too large. Normally that delta E is going to be very small. Okay, but it is nonetheless exists, it is not 0. But let me just take a value. Okay, so 18 micrometer and 10 micrometer will become 8 micrometer. So 18 by 8 gives you how much ratio? It gives you how much ratio? 2 point? 18 by 8. How much? 2 point something. You don't give me this kind of answers. 2.25. So ratio is changing. That certainly has an effect on I. That certainly has an effect on I. Now if I make this bigger transistor, okay, by using many small unit transistors. So even if there is an etching, so if W is becoming, say, how much ratio I want is 2. I was using it 20 by 10. I was using a bigger transistor of W20 and length 10. Now suppose I use small components, 2 by 1 or 4 by 2. So to have a ratio of 20 by 10, 20 by 10, I want a ratio of say 2 10 by 10. Suppose you make it by using 2 unit blocks, each of ratio 10 by 10. And then add them together, their currents I add them together. So how will you write the total current? Total current will be the 10 by 10 plus 10 by 10. So twice of 10 by 10. Twice of 10 by 10. And if 10 becomes 8 in the numerator, 10 also becomes 8 in the denominator. 8 by 8 still cancels out. So you still get a ratio of 2. Are you getting me? You still get a ratio of 2. Yes, Goa campus.
Yes,
Yes,
ma'am.
Nisar.
Yes, ma'am.
I want to know other people's name also. There's a Nisar who's sitting besides him.
I'm Sriram, ma'am.
Shriram. So, Shriram, are you able to visualize?
Yes, ma'am.
Okay, so this is going to be, so even if I have I'm making a bigger transistor 20 by 10 by using two smaller transistors, each of ratio 10 by 10. The 10 is getting overaged away. Similarly, so it becomes 8. So it actually becomes twice of 8 by 8. Even this 8 by 8 cancels out. Okay, that's the reason that we choose a smaller unit component methodology. We are still able to retain the same W by L. We are still able to retain the same W by L. Clear? So normally we choose square components because it is easy for us. Normally we choose square sizes. Okay, so 10 by 10, 5 by 5, 4 by 5. If square is not available, at the most we move on to rectangle. We do not go for any other kind of structure. Okay, so in the layout, normally we prefer square blocks, square geometries. Even if I am making a capacitor or a resistor or a transistor. Okay, normally we prefer the square blocks. If not square, at the most it should be rectangle. Is this clear to all of you how to retain a control on W by Ls? So W by Ls, they help us. Sorry, this unit component, use of multiple unit components helps us in having a control on the ratio. Same thing we do for matching transistors also. Each transistor is made up of numerous multiple components. So that W by L of 1 is same as W by L of. Okay, so two things I have addressed. How to have a control on W by L and how to reduce parasitic capacitance. Now something is left. That is the boundary conditions effect or the surrounding environment effect. Even if you have a control on W by L, still the surrounding environment impact is there. Now think of a situation where you are placing this is your furnace and you are placing your chips that way. Let me draw it so that you can understand. So we have something called, this is a furnace, suppose this is my furnace. I'm not doing a very good design, please bear with me. So this is your furnace and you are placing your chips this way. Wafers are placed like that on a moving belt. And then suppose it is maybe oxygen. Suppose you are flowing in oxygen to create silicon dioxide. So oxygen, as you are flowing the oxygen, maybe oxygen is flown from one side. So oxygen is made to flow from this way. So rate of reaction would be higher here, it would be slower here. This gas would be laden with oxygen molecules. Concentration would be much higher than the concentration at the rear end of the furnace. So rate of reaction is going to be higher at this end and slower at this end. So T-ox growth would be more here in the same time than the T-ox growth here. This is the variations from die to die, wafer to wafer. This can also happen on the same wafer itself. This can happen where you have chips moving from one end of the diameter to it seems the distance is very small, but then it does create a difference. It does create a difference. So you have a change or deviations from wafer to wafer. You have variations from chip to chip on the same wafer. And you have variations from point to point on the same chip. Clear? All this is because of rate of reaction difference. Similarly, think of a situation where you are not placing your wafers separately one from each other, but rather you are placing them in a quartz board in a vertical fashion. Quartz board where you have placing them in this fashion, vertically. Placing them vertically in a quartz board. As you are flowing the gas here, because this area, this is going to be the quartz board over here. Okay, so now rate of reaction would be higher here than the rate of reaction here. Why? Because less gas will penetrate and move in over here. Because there is an obstacle. There is an obstacle, so flow of gas would be little bit hindered. The rate of reaction would be higher at the top and lower at the end, at the bottom on the same wafer itself. So all these things, they cause the change in rate of reaction. So by matching the surrounding conditions, we try to have equal rate of reaction. We try to have equal rate of reaction so that I end up in having nearly same TOX, nearly same overarching effects. Clear? So now if you go for matching, now think of a matching. I have two mosses which are current mirror or differential pair, which are in a differential pair arrangement or in a current mirror arrangement where I need a matching between these two. So what I do, I make each transistor by using multiple fingers. I make each transistor by using multiple fingers. And then what should I do to create a similar boundary condition effects? So what do we do actually? Understand that? So let me take a blank slide so that I can draw on that.